Bayes thinking, Bayes formula, priors, posteriors, in a way that's all there is to say. Once you understand Bayes, the Bayes idea of updating your beliefs about the world, everything else is detail in some sense. This is certainly the way many true Bayesians believe. Maybe important detail, but detail, computational detail, details of choices you make and so forth. The step we took beyond that was talking about Bayes classifiers. So a Bayes classifier basically takes the classification decision and considers the posterior, which is everything you need to know, and makes a weighted decision or a voting decision based on all the hypotheses in the posterior, weighted by the strength of the posterior. And if you do that, and if you believe that your prior is right, and if you believe that the likelihood function family that you chose is right, then in a way this is the best you can do. And the best you can do, which is called Bayes optimal classifier, is not guaranteed to be correct all the time, but is guaranteed to have the lowest average error, or the lowest expected error of any possible classifier, under the assumption that you have the right prior and the right likelihood function. What we're going to do from now on, in the next lecture or two, is still within the concept of a Bayes classifier, but take into account the realities that even if we had the right prior and the right likelihood function, the amount of data that we have may not be enough to I'm sorry, let me take back if we have the right prior. We're going to consider the fact that the amount of data we have is often not enough to fully to have an accurate posterior, and that we need to have a more informed prior. We need to restrict the space in advance based on the modest amounts of data that we often have. So this goes back to this idea of bias. We're going to have to introduce some bias. So let me first help you with the mapping of concepts from the first half of the course, notions of hard bias, soft bias, and Bayesian way of thinking. So we already have hypothesis gets mapped into parameter choice, right? In statistical thinking or Bayesian thinking, you first choose a structure or a family of functions. You may decide that the data came from a Gaussian, or from a mixture of two Gaussians, or from a decision tree, or from some other process we will describe soon called a network or a net. You decide on the structure, on the story, on the overall outlines of the story of how the data was generated. Okay? You can call it generative story, namely a story that tells you how the data was generated without specifying the actual values of each parameter, but just saying this is how the data is generated. It's called generative story. Or you can call it structure, or probability family, probability function family. These are all decisions that are more qualitative. You're not pinning down particular values of parameters. You're just coming up with a space in which you're going to search for the parameter. Okay? I'll explain what I mean by structure in more detail later, but here you can concentrate on the bottom one. For example, Gaussian, or mixture of Gaussian, mixture of two Gaussians. All of this corresponds to, what does it correspond to in machine learning parlance? Hard bias. It corresponds exactly to hard bias. Now what will correspond to soft bias? soft bias is, so hard bias means that you've identified a subset of the space of all possible explanations. We called it here hypothesis space. And it still has many, many members. But you put hard boundaries. You're not going to consider anything outside it. So here, when you choose, the data is going to be explained by mixtures of 3 Gaussians. You're not going to consider anything else, just anything that is a mixture of 3 Gaussians. Still, what the mixture components are, what the means and variances of the individual Gaussians, that you have not chosen. These are your parameters. That's the hard bias. What corresponds to soft bias? That means a preferential treatment of some solutions over others. And we dealt with several different kinds of soft bias. One was a ordering bias. Like in the decision trees, you're considering some solutions before you consider others. So and if you found them consistent, you take them and you don't ever think of the others. In a slightly more refined method, you would consider all solutions, but you will weigh some more than others. Okay, that's the sense of soft bias that I want you to think about now. What does it correspond to here? Prior. The prior, exactly. So prior introduces a soft bias over the space that was beforehand restricted in a hard way. So as a statistician, you make the decision of what structure to use. That corresponds to a hard bias. Now you have a family, typically infinite size, because the parameters are continuous. You have a family of possible solutions. Now you impose a prior on them. That means you impose either an ordering or more likely just a weighing, a prior weighing of which ones are more likely than others. And then comes the data on both sides. And in all the approaches we've used in machine learning before, we used a non-Bayesian way of thinking, where we took the data and we used it to choose one hypothesis solution most of the time. And that would correspond to a map solution. But you now know that the true Bayesian approach does not do that. It just reshuffles the hypothesis space, assigning now a posterior value to each point, whereas before it had a prior value. What I want to talk to you about now is this hard bias, specifically about structure. Because this game is very nice, but if you have a large number of possible inputs and a finite amount of data, you're not going to get very far without making some hard bias decisions. So first we'll talk about a very strong, simple but very strong hard bias that you could always make, and that would do your job, make your further job of estimating the parameters much easier, and that many times is surprisingly good. And then we're going to relax that and make some intermediate hard bias decisions. But it's all going to be, today's lecture is going to be all about hard bias, or in statistical terminology, choosing a structure. So the hard bias decision we're going to make is called the naive Bayes assumption. And don't try to make much sense of the term naive Bayes. It's one of the biggest misnomers I ever heard. There's nothing Bayes about it, except you do use the Bayes formula. But it's not Bayes in the sense of Bayes that I described to you in the last couple lectures. And whether it's naive or not is up to you to choose. But just don't try to read too much into the name. It's just a historical precedent. It's just a name, naive Bayes. You have a function that maps your input space into a set of labels, V. Now the important thing is that the input space, each individual X, consists of many possible features or inputs. They're typically attributes A1, A2 through AN. So you can think about the enjoy sport problem as being one such case. If you remember the enjoy sport problem, the labels are just two, either you enjoy sport or not. So the space V has only plus and minus, or 1 or 0, or yes or no. X consisted of a set of, I think, 6 attributes. So N was 6. And each attribute happened to be either binary or ternary. But in general, The attributes could be continuous. Some of them would be continuous, some of them would be multi-valued, some of them would be single value. Sometimes the multi-valued ones would be ordered values. Sometimes they would be unordered values, like colors. An attribute could be blue, green, red, yellow, and there may not be a natural way of putting an order on them. Typically n would be much larger than 6. This is where this method shines. Where n is very large, it could be hundreds or even thousands, or even more. We're going to look for the map solution, maximum posterior solution. So the map solution, call it V. So V, this is big V and small v is a particular value. V map is defined as that value that maximizes over all possible values of V. So small v is taken from large V. In the case of Enjoy Sport, it's just 2 values. In other cases, it could be more. Maximizes the posterior of V given the input. This is posterior, right? I will write it as argmax. I'll call it V sub j here. So there's an index over the V sub j coming from the big V of P of V sub j given the values of the attributes. And the attributes will be called A1. So what do I call the attributes? I didn't give it an index yet, so that's okay. I'll just call them A1, A2 through AN. So this is for a general x, for any x. Now if there's a specific x, a specific input, we'll give it another index I, and then we'll have to have double indexes here. Aij would be the jth attribute of the ith input. So attribute values have 2 indices. Now I'm going to use Bayes' formula to invert this dependence. So I still have my argmax over Vj, and instead of, remember you can use Bayes' formula for just about any conditional dependence. P of x given y is equal to P of y given x times P of x divided by P of y. Okay, if you think about it that way, and x and y are no longer priors, parameters, something, they're just 2 random variables. You can also call it Bayes' formula. So you don't need to think necessarily about the meaning of Bayes' formula, you can just use the formula here to invert the dependence. So you would have here P of A1 through AN given Vj times P of Vj divided by P of A1 through AN. Is what I did now kosher? Is it true? Can I claim that these are the same? Did I make any assumptions in doing that? I'd like you to be able to formulate your own answer and to feel fairly confident about it. What I did is I took this dependence, instead of P of this given that, I did P of that given this times P of this divided by P of that. The answer is I did not make any assumptions, and it's absolutely kosher, and this is just standard. Next step, I'm going to cross this part out because it does not participate in the maximization decision. Okay? I'm not claiming that this without this is equal to this with it. I'm not claiming that without this I'm allowed to do that. I'm just claiming that because all I'm interested in is maximization, I can do that. Is that kosher? Did I make any assumptions? I see one person committing. Thank you, Tom. Anybody else? Is it kosher? Yes, thank you. Yes, completely kosher. Didn't do anything that required any assumption. All right, my next step is argmax over Vj. I'm going to first write this, P of Vj, so I'm just reversing the order of these two, and I'm going to write this as a product of simpler things. I'm going to write P of AI given Vj, where I goes from 1 to n. So I broke down this thing as a product of probability of one of them given this one times probability of the second, third, and so forth. Is this kosher? Did I make any assumption here? Now I see some dissent. Is it kosher? No, it's not kosher. What assumption did I make? Conditional independence. Can somebody say it a little more explicitly? What exact assumption did I make? Did I make the assumptions that the attributes are independent of each other? Did I make this assumption that P of AI or A7 A3 equals P of A7 times P of A3? Did I make this assumption? Okay. Did I make a different assumption? What assumption did I make? They are independent given the value of V. Do you remember our discussion of conditional independence? What I make here is a conditional independence assumption. And just like independence assumption. And just like it takes 2 to tango, it takes 3 to make a conditional independence assumption. Conditional independence is independence of A on B, condition on C. So when we make a conditional independence assumption, we need to understand exactly what A and B and C are. What is the conditional independence assumption I made here? Yeah. What is independent of what? Condition on what? Yes. Yes. Any pair of attributes, so I made many conditional independence assumptions, one for every possible pair of attributes. Every pair of attributes is conditionally independent of each other, conditioned on which random variable? B. The label. Condition on the label. Okay? That's the assumption we're making. For every I1, I2, and okay, for everyone in I2, AI1, AI2 are conditionally independent given. By the way, you can't just write conditionally independent. If you say the words conditionally independent, you have to follow it by the word given. And conditionally independent of what? Tom?
Is this every pair or every subset?
That's a very good point. That's a very, very good point. It's not the same. You can have a situation where a pair of attributes are, every pair is independent, and yet subsets are not independent. It's called the absence of second order correlations or effects, but you can have higher order correlations. Now, naive Bayes, the assumption you're making is somewhere in between. Somewhere in between. I don't believe that it's exactly every subset. It's certainly not just every pair. So I'll get to it in a minute. Let me just write it down here. Conditional independence given V, given the random variable V, which means that for every I1, I2, and Vj, P of AI1, AI2 given the V is Vj, is equal to probability of AI1 given that V is Vj times P of I2 given Vj. I'm just spelling out for you what conditional independence means. Now, let's see what independence assumptions we actually had to make in order to get to this conditional form. If instead of using this conditional form, I use the chain rule, that means I would have P of A1 given Vj times P of A2 given A1 and Vj times P of A3 given A1, A2 and Vj and so forth. So the dependence of A1 and A2, to try to answer your question, is already taken care of by looking. This is A1 through AN, A1 through AN here. The way I think about it is you have sort of this triangular relationship. To take out, let me do it on the board. I'm not sure I have the right, I mean, you may be right that it's every subset, but let me tell you what I'm thinking, and maybe we can figure it out together. If I did not make any approximations or any assumptions, P of A1 through AN given V can be written as P of A1 given V times P of A2 given A1 and V times etc. So P of AI given A1 through AI minus 1 and V all the way to P of AN. Okay? So, if you ask what assumptions did I make here, well, I converted this into P of A2 given only V. Right? This is the assumption I made. This product does not make any assumptions. Chain rule can always be applied. So the assumption I made is I approximated this with this. Well, that's the assumption that A1 and A2 are mutually conditionally independent given V. Right? When I get to here, I approximated it by AI given V. So this makes the assumption that AI is conditionally independent of A1 through A minus 1 as a set given V. Right? You can think of these as one variable. So the actual condition dependent assumptions I made are a little, they're certainly not one-on-one, you're right. But I'm not sure that you need all sets. I mean, the strongest assumption is that every subset is independent of every other subset, given the label. And I'm not sure whether the assumptions I made here are quite as strong as that. They don't appear to be as strong, but it may turn out that they are effectively the same.
Well, it seems like if there is a subset which doesn't follow this conditional dependence rule, then the full probability distribution over there, the probability of A1 through AN, given Uj, is not equal to the product of all the attributes independently. Like if there is a subset, then you can't say that any of them are independent. But I don't see this argument fails on that.
Well, this does not prove my point, and your argument might prove yours, so let me think about it for a moment. You're saying that if there are two subsets, subset 1, subset 2, such that they're not conditionally independent, then there would be some values for which P of S1, S2 given V is not the same as P of S1 given V times P of S2 given V. Right? And S1 and S2 are some subsets of all the attributes. So my only concern is that there are other variables here, and that we're averaging over them. I'm not sure I have the right intuition for that. You may very well be right. Should go back to the book and find out. Do you guys know the answer to that?
I mean, I feel that they should be independent of each other.
Any subset?
Yes.
Okay, it might be true.
The baseline structure from the baseline
Yeah, if you're right. If you draw the net, and then you can conclude from that. If you draw the structure, yeah, and we will do that in half an hour. So you're probably right. Okay, so the bottom line is we're making conditional independence assumptions. They're always conditioned on the label, and they're very strong assumptions. They're basically saying that the individual attributes can be treated separately when they're viewed as being generated from the labels. So this is an interesting interpretation I didn't give you yet. When we used Bayes' formula to invert the dependence, instead of given the attribute values, given the input, give me the output, given the probability of the output, we inverted it to given the output, give me the probability of the inputs. This is a kind of a change in the way of thinking. Our original way of thinking was first there are attributes, and we don't know how they're generated, and we don't care how they're generated because they're given to us, so we don't need to estimate how the probability of generating those inputs. We don't need to estimate the function from which they were generated. And given those attributes, we only are trying to estimate the probability of the label being one way or another. There are methods to do that without ever considering the underlying distribution of the input. They work by looking at the directly at estimating things of this sort. Okay? But that's not what we're doing. Using Bayes' formula usually entails that we're inverting the way we think about the problem. Instead of thinking about the input generating the output, or the input generating the label, we think about, in a way, the label generating the input. And the way we think about it is we're saying there may be two labels, and one label tends to, quote-unquote, generate one kind of distribution over the inputs, and another label tends to generate a different distribution over the inputs. Sometimes it corresponds to the real world. It makes sense in the real world. Example, symptoms of a disease and identifying the underlying disease. Let's say you have a choice of two, some disease and not being sick. So cancer, no cancer. If you have cancer, it tends to generate a whole set of symptoms. Fever or no fever, pain or no pain, headache, elevated blood counts of something, 100 different features. And they're not deterministic. But given that you have cancer, there's a certain distribution over each one of them. If you don't have cancer, there's a different distribution over the set of these symptoms. Right? Now, when we come to classify, we momentarily reverse it and say, oh, first there are symptoms, and the symptoms give rise to the classification, to the diagnostics. But going through Bayes' formula brings us back to a view that makes more sense medically. No, first there was the fact whether you have cancer or not, and from that the symptoms were derived. So doing this conceptual inversion here makes a lot of sense from a medical point of view. Other times that won't be the case. Other times really the logical way of thinking about things is the input generates a label. And nonetheless you could do it mathematically. So whether it makes sense from the domain point of view or not, we do think when we do a map classification, we do think as the label as generating the input, which is what we're doing here. The label generates the input. When I say by generating the input, I mean that for a given label, there's a distribution of input values that is derived from it. Now the assumption we're making is that given the label, each input attribute is generated independent of all the others. Okay, why are we making that assumption? I erased this thing, but we had it here. It gives us the hard bias. That's what we're looking for. It reduces our space considerably. Why is that so? Because this formula in order to use it, we need to come up with the actual numerical values of all these p's. Okay? Now let's say we have J labels and n attributes. How many probability estimates do we need to come up with? How many parameters does our model have? Well, the prior, this is the prior over the labels, has how many degrees of freedom? How many parameters? J, or one could say J minus 1. So there's some arbitrariness to how you count parameters. You could say J minus 1 because they have to sum to 1. So how many parameters are there in characterizing the probability of head or tail of flipping a coin? Well, there's probability of head and there's probability of tail, but they have to sum to 1, so we tend to think about them as 1. Right? So the degrees of freedom, there's just 1. If you toss a die and has 6 faces, and you have to characterize probability of it falling on each one of these 6 faces, you could say 6 parameters, or you could say really there are only 5 parameters. The 6th one is determined by the 5. So let's just assume for our sake of our discussion and also for the sake of your homework that we call it 5. Namely, the number of degrees of freedom rather than the number of formal parameters. So this gives rise to J minus 1 parameters. What about this? How many parameters do you see here? For every value of J, for every label, you have a different distribution over all possible values of the attributes. Now, I didn't tell you whether the attributes are binary or ternary or something else, so actually you couldn't answer me fully. Let's assume for a moment that the attributes are binary. So if the attributes are binary, every attribute AI has 1 degree of freedom, probability of head, for every label, J. So that would give us n attributes times 1 degree of freedom times J labels. So that's n times J. In general, it would be n times the number of possible values that the attribute can take minus 1. So for a binary attribute it would be 1. For an attribute that takes on 10 values it would be 9. So I'd call it the size of the AI, the A, times J. But in general it's on the order of n times J. And let's take for a moment with binary attributes just so that we can make the right comparison. So n times J plus J minus 1, it's about n times J. So that's the number of parameters. It grows linearly with the number of attributes and linearly with the number of labels. Now compare that to not having made this assumption. Suppose we stuck here. Here you still need the J minus 1 attributes, J minus 1 parameters. How many parameters do you need to characterize these distributions? First, there's a separate distribution for each J, for each label. So that's J times something. In that regard, we're the same. How many parameters do you need to classify a distribution of a joint distribution of n binary variables? Sorry?
Every subset to power n.
I'm sorry?
Every subset which is to power n.
2 to the power of n, roughly. Why? Because if you're trying to define a distribution over, let's say, vectors of n bits, there are 2 to the n such vectors, and any distribution is a priori possible. So it is like specifying a multinomial distribution over 2 to the n possible outcomes. It's like having a die with 2 to the n faces. And any set of 2 to the n numbers that sum to 1 is a fair candidate. So actually it's not 2 to the n, it's 2 to the n minus 1, because they have to sum to 1. But it's about 2 to the n. So to do the full, to not impose any hard bias, not impose any structure, we need on the order of 2 to the n times J parameters. When you make what's called a naive Bayes assumption of independence of attributes of each other conditional on a label, we're down to j times n. So if you forget about the j for a moment, let's say j is a small fixed number, it's a number of labels, it could be 2, it could be 3, it could be 10. Forget about j for a moment, you go down from 2 to the n to n. That's a huge drop, right? If n is 1,000, it's from estimating 2 to the 1,000 parameters to estimating 1,000 parameters. Which means if you have 1,000,000 data points, you could estimate 1,000 parameters, but you can't estimate 2 to the 1,000 parameters. So this is driven by necessity. You have a finite amount of data, you have a large number of attributes, you cannot afford to estimate an exponential number of parameters. Now suppose data was no limit, no limitation, and computation was no limitation. Suppose you could have as much data as you want, and you have as much computation as you want. Then there would be no reason to go to the naive Bayes method. Even if the naive Bayes assumption were completely correct, not making it would not hurt you if you had infinite data. Right? It's as if you want to find a polynomial that passes through your data points, and the true polynomial is of degree 5, but you insist on using a polynomial of degree 27. But if you have a lot of data, and it's accurate data, you will end up with effectively a polynomial of degree 5. All the other coefficients are going to be 0. You will zero in on the right answer if you have infinite data. But that's hardly ever the case. In reality, you don't have enough data. And if you assume a 27 degree polynomial, you will get a very noisy picture. Whereas if you assume a lower degree polynomial, let's say you assume a 4th degree polynomial, even though the real answer is 5th degree polynomial, you will get some kind of approximation that will not be perfect, but it might be better than the 27th degree polynomial, because the 27th degree polynomial would overfit like crazy. Maybe that's not the best example, because in case of polynomials with 6 data points, you should nail it down completely. But in general, what assumption you make about the structure, or what kind of a hard bias you use, has to match how much data you have. If you don't make any assumption, you typically do not have enough data. And therefore you didn't commit any sin in choosing your hard bias, but then your map solution would not be very good, because you just don't have enough data to capture it. If you use the hard bias that's too strong, and you restricted yourself, you may not end up with a very good solution either. The one thing that saves us in the case of naive Bayes is that we're not interested in estimating these accurately. We're only interested in finding out which label gets the maximum value. So the assumption we make in naive Bayes is often just not true. It's a very bad assumption. And yet, the classification decisions that we get out of naive Bayes are often surprisingly good. This has been observed in practice well before people try to understand it. Sometimes you work with data that you know does not satisfy the naive Bayes assumption. You know that the attributes are not independent of each other. Most real-world data, the attributes are not independent of each other. If you go back to the medical example, having fever and having a headache are not independent. Or having some biological markers or blood tests or whatever, they're not independent of each other. So if we were to assess the naive Bayes assumption in terms of estimating these things, the probability densities of the different symptoms, they may fail miserably. They may just be wrong. But we're not doing that. We're only using that assumption to order the different hypotheses and choose the one that's highest. If you assess it by how well it chooses the one that's highest, naive Bayes assumption often works surprisingly well. And there's been quite a bit of work in trying to explain why it works so well, even though the underlying independence assumptions are not true. So when I say structure, I'm going to give you a graphic representation of the structure in a short while. But what I mean is exactly what independence assumptions you're making. It usually boils down to independence assumptions, which in turn boils down to a hard bias. After you threw away, or after you put in all the independence assumptions, anything you did not assume, you assume there may be some dependence, and then that boils down to parameters. And the prior over parameters corresponds to soft bias. Questions? One other thing that's very nice about naive Bayes is it's extremely easy to implement. It's really, really easy to collect the values of attributes, sort them by the label, collect for each attribute and each label how much of the data for that label had this value of the attribute, had that value of the attribute, come up with these factors, come up with this factor, and then the actual looking at test data and making the decision is very quick, very fast. So you can write this much code that was captured naive Bayes. In fact, we often do that in this class. We're not going to do it this time, but you're still free to do that. Look at previous year's assignments. It's really, really very simple code and very easy to understand. So it's very attractive. It's a little easier to write than neural networks, maybe slightly easier even than decision trees. Very easy to try, and it works surprisingly well. So it became sort of the third standard tool of machine learning. You know, any problem you look at, decision trees, neural networks, naive Bayes. It's the first three things you try. There are still some subtleties. Let me go over some examples with you using the slides. So here's the naive Bayes algorithm. It takes as its input just examples, 20 examples, which consist of a set of attributes and a label, another set of attributes and label, input and output, sorted out by the target value, the target label Vj. For each j, estimate a prior of Vj, and you can do that by just relative frequencies of the different labels in the data. So if you're classifying into cancer and non-cancer, you just observe that 0.8% of the data had cancer and the others don't. And then you do something a little bit like a double loop instead of a single loop. For each label Vj and for each attribute type AI, you estimate the probability of AI given Vj. So the second factor is there. This is the part where we're going to talk about a little bit more. But once you did that, you have the prior over the labels, and you have the likelihood of individual attributes given the label. And now, classifying a new instance just corresponds to calculating this and keeping track of which j gives you the maximum. And this NB here stands for naive Bayes, the naive Bayes answer. If I need this example, our biggest issue is going to be in estimating these factors, this P of AI given Vj. So suppose you're in a situation where for a given value, a given label j, a particular attribute never was observed with a particular value. So much easier to just do it here. So typically you would estimate P of AI. Let's say AI is a binary, so AI means AI equals 1. given Vj as the count, how many times you saw in the data an input-output pair with AI having value 1 and label Vj, divided by how many times you saw in the data the label Vj. Does that make sense? Estimating probability of AI given Vj is the count in the training data of how many times you saw them together divided by the counter data of how many times you saw Vj. What kind of estimate is this? What is it called? This is the maximum likelihood estimate. Okay? It's also called relative frequency. But as I told you, most times, in most simple cases, maximum likelihood boils down to relative frequency. So this is the maximum likelihood estimate. Now, maximum likelihood estimates I spoke very positively about. They're wonderful. They have lots of good properties, but they have one known weakness. They're not very good to use when you have very small numbers, very small counts. If I take a coin out of my pocket and flip it once, and I get head, a maximum likelihood estimate would say the probability of head is 1, probability of tail is 0. And I hope you don't accept that as a good estimate. It's a very bad estimate. But not only if I flip it once, if I flip it 3 times and I use the relative frequency, these 3 could all have been heads. And that doesn't mean the probability of tail is 0. Right? So maximum likelihood estimates are known to have great variance for small counts and to produce answers including 0 estimates. And 0 estimates are very particularly bad because we often work in log space, and taking the log of a 0 estimate takes you to negative infinity and basically kills anything you're trying to do. So maximum likelihood estimates should not be used when you have small counts. They should be smoothed somehow. There are many ways of thinking about smoothing. One way of thinking about it is the simple-minded way is just avoid zeros. Okay? So people use things like putting a floor, saying the estimate could not be less than 0.1 or 0.01. That's fine. Another way of thinking of smoothing is in the terms of statistical estimation theory that we talked about, notions of variance and bias. By using maximum likelihood estimate, you're using an estimate that has a 0 bias, but it has quite a large variance, especially with small counts. By smoothing it, you are reducing the variance at the cost of increasing the bias. And as we said, sometimes it makes sense to use one to pay for the other. The third way of thinking about it is the Bayes way of thinking about it, which is don't use maximum likelihood estimate in the first place. Come up with some kind of a prior over the probability of head of a coin, and then use your data to update a prior and create a posterior. It's the last 2 ways of thinking that I'd like you to think about. The reduction of variance, which is often called shrinkage in statistical literature, or the Bayes way of thinking, which is you need a prior and don't even think about maximum likelihood, just use a prior and produce a posterior. So a very commonly used method for solving the problem of not getting zeros is to modify the formula by introducing what we had called earlier in this class pseudo-counts. Remember when we talked about estimators, we said if you flip a coin 10 times, let's pretend that we also flipped it 2 more times. One of them was head, one of them was tail. This way we're sure that we don't have zeros. These are called pseudo-counts. They're not like the real counts you got from the data. They're counts that you've gotten out of nowhere. Here are the pseudo-counts. These are the actual counts. So n would be the total number of data items that were seen with label J, and n sub c would be the total number of data items that were seen with label J and AI had particular value. And you add pseudo-counts to both sides. The pseudo-counts could be integers, which was what we discussed until now, but they could also be fractions. The only thing you have to make sure is that when you sum over all of these, they sum to this one. In this particular case, the parameterization was presented in such a way that P is some kind of distribution over the AIs, maybe uniform, maybe something else. It's a prior estimate for this. And M controls how big the pseudo-counts are, or how much smoothing you're going to do. There are other ways of parameterizing it. The important thing is that you have a degree of choice in choosing how much to smooth. And that corresponds exactly to the variance versus bias. In one extreme, you don't smooth at all, in which case you introduce no bias, but your variance is not controlled, and you may get zeros. In the other extreme, you can use pseudo-counts that are very, very large. If these numbers are much larger than these numbers, you're effectively sticking with your pseudo-counts, and the influence of the actual data on it becomes negligible. That corresponds to introducing a strong bias and having very, very low variance, because variance depends only on the real data. And if the real data makes very little difference, it's like deciding in advance the probability of flipping a coin is 0.4 and ignoring the data. So, looked at from the frequentist point of view, this controls the variance versus bias. Now there's also a way of looking at it from Bayesian point of view. And from a Bayesian point of view, this corresponds to a particular choice of a prior. There's a family of priors over binomial distributions called beta distributions. And having these pseudo-counts here corresponds to having a prior from the beta family, and the actual choice of the parameters here corresponds to which member of the beta family is used. And again, the family spans the whole range of, is it a prior that insists on all the mass being in a particular area, and then you need a lot of data to get out of that area, right? Because if you have a strong prior, a very sharp prior, that means you have a strongly formed opinion before you saw the data, and you'll need a heck of a lot of data to move away from that opinion. That corresponds to the high bias, low variance. Or a very weak prior that gives you a little bit of an opinion but is easily swayed by data. That corresponds to less bias, more variance, and smaller numbers here. This may look like a small technical point, but actually a lot of estimation hinges on, the qualitative estimation hinges on the exact choice of these parameters. So there's been a lot of work in many different domains on doing better smoothing, either using the Bayesian formalism, using the frequentist formalism, or using no formalism at all, just trying many different things. When you deal with hundreds or thousands of attributes and millions of data points, you're dealing with small counts all the time. Things that occurred 0 times, 1 time, 2 times, 3 times dominate. And it's very important how you choose to handle them. Questions? I want to tell you about one of the most common and successful uses of naive Bayes classifiers is in classifying text. It's been done and continues to be done all over the place, and very successfully. If you take, let me just, the slides and the book have much more detail on how to do that. I'm going to skip that, but I want to show you just the experiment that was done. Newsgroups form a natural hierarchy. You can see here an example of 20 different newsgroups. This is from more than 10 years ago, the data. You can see that they form, there's a hierarchy that can be implicit in the names. This is all comp.something, rec.something, science.something, and so forth. These are 20 different newsgroups, and somebody pulled 1,000 different postings from each one of them. And the idea was, using that as training data, can you train any kind of classifier that, given a new posting, would automatically tell you which bulletin board it came from, or which net news group it came from, or it should have gone to. There are lots of problems with this setup. For one thing, some of the articles are cross-posted, so they're posted to more than one. Second, there's no clear definition of ground truth. What's ground truth? Whatever I compose a post and I post it someplace, somebody else might have posted it somewhere else. So you could take as ground truth wherever it was actually posted, but there's some intrinsic noise in that because it's a human decision where to put it. So all of these issues are kind of cloud the picture, but nonetheless, most people would agree on the classification of most postings. So if you were exposed to 1,000 postings from each one of these 20 news groups, you would develop some sense of what these news groups are about, and you would be able to classify new examples in agreement with other people. Now, I say if, but in reality, nobody would read 20,000 postings, right? So there's some things that you would get out of it after reading the first 2 or 3 or 4 or 5 postings that would be enough for you. Or maybe you don't even have to read anything, you just look at the name. But the name may be misleading. It could be that the net news group was created with some intention, but in practice it's used for something slightly different. So there are advantages and disadvantages to the human way of looking at it. Be it as it may, this was used as a standard test bed for testing many text classification algorithms. And naive Bayes performs very well here. 89% classification accuracy. 89 may not seem like a lot, but remember, this is not binary classification. This is 20-way classification. In binary classification, a random choice would give you 50% accuracy. In a 20-way classification, a random choice would give you 5% accuracy, assuming uniform prior. So 89% is not bad. Let me show you how it fares relative to other classifiers. By the way, here's an example of one posting from the article rec.sport.hockey. I didn't tell you what the attributes are. Remember the A1 through AN? Can you guess what they are? Words. The occurrence of particular words in a document. So if you only consider the 100,000 most common words in English, you have 100,000 attributes. And each attribute could take on the value 0 if the word didn't occur, or 1 or 2 or 3 or more if it occurred more than once. Here's the performance of naive Bayes relative to several other classifiers. What you have on the y-axis is the accuracy on test data. What you have on the x-axis is the amount of training data used to train all these classifiers, up to a total of 20,000, which is right here. This is a log scale. 20,000 is here means 1,000 per NetNews source. The assumption here was that there's a uniform prior, and even the training data was selected to reflect that. In the real world, the prior may often not be uniform, and in fact in the real world your training data may not conform not only to uniformity, but also may not conform to the prior. In other words, your training data may have a different distributions of labels than what you anticipate. That could happen. The naive Bayes method allows you to handle that separately. You can train this part or this part, the prior over the labels, separately, or you can even not train it, just impose it using some external considerations. So you can separate the issue of the prevalence of the labels, prior prevalence of the labels, from the issue of estimating the distribution of attributes in a label. So all the methods perform, let's say in the gross scheme of things, very comparably. And they all, of course, perform better as you get more data, and they begin to asymptote around the high 80s or 90 as you have this much data. And one could speculate and actually try what happens if you have a lot more data. And the answer is it will not get to 100% for the reasons that I mentioned earlier. That's one of the reasons. So in situations like that, you ask yourself, what is the upper limit? And one way to get a handle on the upper limit is to look at how well people perform. So you can take 3 different people and sit them in different rooms and give them the same test set and have them annotated, and then compare the results and ask yourself how often do they all agree. This is known as the inter-annotator disagreement rate. And generally, in most situations, that disagreement rate can be looked at as an upper bound, or rather the agreement rate is an upper bound on the accuracy of classifiers. If people cannot agree, then in what sense would the machine do better? Now, it's possible that machines will do better than people in general in tasks, but if the correct answer is defined by people, then the inherent inaccuracy of people who decide what the correct answer is is a limit on how well the machine could do. You know, if people say deliberately flip the answer, the correct answer, every 2% of the data, then there's no algorithm that would do less than 1% error, because on those 2% they will be at most 50% right. So that puts a limit. But beyond that limit, there are other reasons that naive Bayes is limited. Naive Bayes only considers the occurrences of words and considers them independent of each other. And one could argue that in difficult discrimination cases, just looking at the set of words that were chosen and ignoring the order in which they occur, or ignoring second-order correlations and third-order correlations between the different words, loses some information. There have been many attempts to do better than naive Bayes in text classification, and they have not been very successful. There are some. After this work was done, there's some work that we're going to talk about briefly called SVM, support vector machines, that seem to do slightly but consistently better than all these methods. Just to tell you what these methods are, the one called Bayes here is actually naive Bayes, and again it's a terrible name. It's not really a Bayesian approach. The one called TF-IDF and PRTF-IDF are taken from the field of information retrieval. TF-IDF stands for term frequency inverse document frequency. It's the most prevalent method of doing information retrieval, and the one with the PR in front of it is taking that method, which was an ad hoc method, not derived from any formal theory, and trying to probabilize it, to make it a probabilistic, so changing it a little bit to give it a probabilistic interpretation. In the grand scheme of things, they all work kind of comparably. The naive Bayes seem to start a little bit below, and then as you get more data, moves into the higher part. But the probabilistic TF-IDF seems still a little bit better. I want to tell you about another method that was used that's kind of funny and cute. That I think Tom Mitchell is the one who tried it, although I think people have talked about it before. It's very simple. You take those 20 news groups, you take all the training data, separate it into these 20 news groups, and you use the Unix compress utility to compress it. Okay? That's all you do for training. You take your training data for each one of the 20. And you compress it to occupy less space. So some of them would compress more, some of them would compress less. But that doesn't matter. They all compress a good amount. And then, to classify a new instance, you attach it to the end. Your new document, you attach to the end of your training data for each one of these 20 news groups. And you compress again. And now, that compressed document sits here. Right? If you know something about the kind of compress that Unix uses, it's based on the Lempel-Zeev algorithm, which is an adaptive compression algorithm. Which means as you go through the data and compress it, you keep track of what are the most commonly occurring sequences. And you constantly readjust your coding for the compression to assign the most commonly occurring sequences a smaller representation. And then to decide how to classify this new orange document, you only look at the length of this part, of the additional part. So the idea is that if a document, the test document, looks more or less like your training, if the kind of strings in there, sequences of words and characters and whatever, are the kind that occurred a lot in the part that preceded it, then it will be compressed better. So whichever one gave you the smallest additional amount in the compression is the winner. It did as well as everybody else. And it didn't require writing any code, just running the compress utility 20 times and then again 20 more times for every test document. This is something you find a lot in classification work. There are a million methods, and they all agree to they all have similar accuracy to within 1 or 2%. It's very rare and very difficult to come up with something that would do significantly better. Not that people don't try. And part of the problem is that you don't know what your upper limit is. It's not 100%, it's less than that, and you don't know if you're near that or not. Questions? Okay. We are still behind. So let me just introduce Bayes nets and talk about them a little bit. So we're still talking about structure and hard bias, and I gave you a very radical solution, about as radical as you can make it. I make every attribute independent of every other combination of attributes given the label. And that reduces the number of parameters we have to estimate from 2 to the n to n. Sometimes that assumption is too radical, too restrictive. I mentioned that many times even when the assumption is not correct, the classification comes out of it is good. But there are times when even that's not true. There's just there is strong dependence, and making the dependence assumption just doesn't work. If you only had a choice between 2 to the n, which is called sort of the full Bayes or the full joint probability modeling, and the n, that's not good. Full 2 to the n is not feasible. You don't have enough data. Just n may be too strong a restriction. What we want is to be able to do something in between. And furthermore, we want to be able to use our knowledge of the domain to decide what dependencies exist and what independencies exist. Bayes networks, also known as Bayes belief nets, also known as Bayes nets, also known as graphical models, do exactly that. They're formalisms that allow you to specify explicitly which of your parameters depend on which other parameters. And by doing that, you allow yourself you end up with a number of parameters that's somewhere between n and 2 to the n. Maybe it's polynomial of a low degree, or maybe it's something else. Remember, n and 2 to the n ignore the j factor, the number of labels, and also ignore the number of different values that each attribute can have. But still, very roughly speaking, naive Bayes is a linear number of parameters. Full Bayes, a full joint distribution, is an exponential. And what you want is to be able to work with something in between. And you also want to not make a wholesale decision. You want to make a decision judiciously based on what you know about the domain. So here's an example of a domain. Kind of a famous example, a very nice one. What you have here is a bunch of binary variables, 1, 2, 3, 4, 5, 6, and they tell a story. They tell a story of a fire that may or may not happen in a forest, starting from the bottom. And that fire, in terms, the probability of that fire happening depends on whether there was lightning the night before or that night, because lightning can start a fire. But it also depends on whether there was a campfire, whether the group of people camped in that forest and had a campfire there, because that often starts a fire. And it also depends on whether there was a storm, because a storm can put out fires. But that's not the only thing that's happening here. There are other dependencies. If there was a storm, that changes the probability that there was a campfire, because people tend to not camp out and have campfires if there's a storm. They might stay home, right? And there cannot be a campfire if there was no bus tour group. Or maybe there can be, but it reduces the probability. If there is a bus tour group, it increases the probability there was a campfire. And furthermore, you may have access to the information of whether it thundered or not. And that may tell you something about lightning. Okay? So what I'm showing you there is actual dependence relationships. What influences what? And this is a directed graph, which means it also talks about causality. What causes what? So one way to think about it is to start here. There are some things that are given, whether there's going to be a storm or not, and whether there's going to be a bus tour group. And then there are other things that are not fully determined, but at least influenced by the choice of these things. Storm, whether or not the storm determines the probability there will be lightning and the probability there will be campfire. Probability of campfire is determined by both of these things. Forest fire is determined by this, not deterministically determined, but strongly influenced by these three things and so forth. What you see explicitly is dependencies. And there are quite a few of them. What you don't see are the independencies. And there are many more of those. A Bayes net or a graph explicitly lists dependencies, but there is a way of reading the independencies from it. And in fact, a BaseNet only lists direct dependencies, but there are actually indirect dependencies as well. So you can ask yourself, is forest fire dependent on the bus2 group? And the answer is yes. But there's no direct link between them. So there could be independencies that are indirect in the graph. The general rule for reading independencies is that every node is independent or conditionally independent of everybody except its children, given its immediate parents. So since information flows in a directed graph down in this case, you take every node, you make it dependent on its parents, and then conditioned on its parents, and then conditioned on its parents, it is independent of everybody except its descendants. So the formal definition is, each node is asserted to be conditionally independent of its non-descendants given its immediate predecessors. That's a mouthful. Now in this small network, we can work out a list of conditional independencies that happen here. In networks of hundreds of, even fewer, let's say 20 nodes, the number of conditional independence assumptions that are made implicitly is exponential. And every time we make a conditional independence assumption, we get rid of one parameter. So we go down from the 2 to the n towards a much more manageable number. This is what I meant by the word structure. In the case of graphical models, the structure can be captured by a graph. There are other families of distributions and statistics that have other structures. But generally, structure corresponds to making this kind of hard bias assumption about what depends on what. The soft bias will be captured by the actual dependence. If you know that this depends on these two, you still want to know how it depends on it. So every node has associated with it a table that specifies the distribution of the value of that sitting in that node as a function or conditioned on the values of the parents. In this case, all the nodes are binary, and here we have a campfire, that's C, so either there was a campfire or there was no campfire, and here you have all possible values of the parents. Either there was a storm and a bus tour group, or there was a storm but no bus tour group, or no storm but bus tour group, or none of the two. And for each one of these, the table specifies the distribution of values over the campfire. In our case, it's binary, so you still have to sum to 1. This kind of table sits on each one of these. Now, this thunder guy has only one parent. So the table will correspond to only 2 values here, either lightning or no lightning. Right? Campfire has 2 parents, so the table would have 4 columns for every possible combination of the values of the parents. Poor forest fire has 3 parents, so the table will correspond to 8 conditioning events, and each one of them distribution over 2. But you can see how this can be generalized to non-binary variables. If it's non-binary, you may not be able to express it in the table. You may have to have some analytical distribution, but it will depend on all your parents. So these may not be binary, and this may not be binary. There's a version of BaseNets that's called acyclic network. I'm sorry, not acyclic, a non-directional network where you don't have arrows. The mathematics of it are slightly different. The intuition behind it is less of cause and effect and more of a joint distribution where everything affects, in principle, everything affects everything else. You could calculate in principle how many parameters are needed to fully specify this model. So to fully specify the distribution here, you can count the number of parameters here, and remember what you want is to count the number of degrees of freedom, not actual number of parameters. So for example, right here, there's 1 degree of freedom. So here you have a total of 4 degrees of freedom. Okay, or 4 parameters, 4 independent parameters. in any Bayes net that I give you, depending on whether the parameters are binary or ternary or whatever, and depending on the topology of the network, you should be able, in principle, to calculate how many parameters you have. You would typically find, if the network is not too connected, the number of parameters is manageable. There's maybe a small polynomial. So in the continuum between naive Bayes, that is n parameters, and full joint distribution, which is 2 to the n, it sits closer to the naive Bayes, which you have to, given the finite amount of data we have. We'll come back to this and discuss how do you determine these parameters and how do you use these parameters to do inference next time. But hopefully you have enough to do your homework. I'm not sure. I didn't finish talking about it, so I'm not sure. Do we have enough to do all the homework?